Hello everyone. So today's topic will be support vector machine. Support vector machine is a supervised machine learning algorithm. Is a is a supervised machine learning algorithm. And it is used for both classification and regression. For regression, it is known as SVC. Yes, sorry. For regression, it is known as SVR, support vector regressor. And for classification, it is known as SVC, support vector classifier. This is regressor. This is classifier. Support vector machine is mainly used for classification. It is preferred for classification tasks, not much for regression tasks. So what does the support vector machine does? How does it classify? Let me elaborate with a graph. Consider this one as x1. X-axis is x1, some feature, input feature, and x2. These are input feature 2. X1 is the input feature and x2 is also the input feature, that is independent variables. So we have binary classification task. Let's say binary classification. These are the points we have. Okay. And this is class 2, class 1. So what the support vector machine does is it first draws the best fit line, which will classify, which will make the classification. This is the best fit line. So now the best fit line makes the classification. Along with the best fit line, the support vector machine, along with the best fit line, the support vector machine will draw the marginal planes. This is the marginal plane. Along with the best fit line, the support vector machine will draw the margins, two margins, one above the best fit line and one below the best fit line. Okay. And if you notice here, the margins will pass through the nearest points, nearest data points. See, for the X class, it has passed here. For the O class, it has passed here. It will pass through the nearest data points. These are known as support vectors. This is known as support vectors. The data points on which the margins will pass are known as support vectors. And the goal of the margin is, what is the goal? How the support vector machine will draw this margin is the distance between the margin and the best fit line. The distance between the margin and the best fit line should be maximum. It tries this distance to maximize. the distance should be maximum. That is the goal. That is the goal of the support vector machine. The best fit line, along with the best fit line, it will draw the margins with the support vectors, the nearest data points, and the goal is to keep the margin maximum. So what is this best fit line along with the margin is known as? I will draw one more diagram for you. So this is the best fit line, and these are the margins. So together, the best fit line and margins together, this is known as hyperplane. This is known as hyperplane. So support vector machine draw the hyperplane. It will identify the hyperplane to make the classification. There are two types of margins. One is hard margin, and another is soft margin. So what is the difference between the hard margin and soft margin? See, this is a linearly separable data. Linearly separable. Very clear. That means no overlapping. We can clearly make a division between X class and O class with our hyperplane. With our hyperplane, we can clearly make the separation. So this is known as hard margin. Then what is the soft margin? See, this is our best fit line, and these are the margins. This is our hyperplane. But if you notice here, some of our data points are overlapping, though it is linearly separable. Here also the data is linearly separable, but data is overlapping. If you see these points, these are overlapping, right? So such, and we have drawn the hyperplane on that. So this is known as soft margin, where the data is overlapping and there will be chances of error or misclassification because of overlapping. So this is the difference between soft margin and hard margin. we have the hyperplane. This is hyperplane. So what is the equation? What is the equation of hyperplane and what is the definition of hyperplane? Hyperplane is nothing but it is a decision boundary. We can call it as decision boundary that separates the different classes. Hyperplane is a decision boundary that separates the different classes. And equation of hyperplane. If you Google it or if you ask to ChatGPT, I don't want to go into the in-depth max tuition for this. So let me give you the equation directly, and we will further because we will focus more on finding the cost function, because we have to find the best hyperplane. So we will focus mainly on the cost function. So the hyperplane equation, if you Google it, you will get the hyperplane equation has W transpose, T is transpose, X plus B. You can see this is the equation. W transpose of X plus B is equal to 0. This is the equation of hyperplane, where W, what is W? W is weight vector and B is bias. Okay. And if the hyperplane goes downwards, of the margin, this is known as, if we will classify this as -1. This class, which is the downwards towards the hyperplane, is -1. And the upwards to the hyperplane, the class we will classify as +1. This you have to know. And this is the equation. W transpose of X plus B is the equation of hyperplane. So if I write the function f of X is equal to W transpose of X plus B. Okay. And if f of X is greater than 0, then class 1. And if f of X is less than 0, then class is -1. F of X is greater than 0, then class is +1. If f of X is less than 0, then class is -1. That's all. And if I apply the class, how it will look? If I will write together with the y, I will call it as yi of W transpose of X plus B. This is the function. If yi is equal to +1, then W transpose of X plus B is greater than 0. If yi is equal to -1, that is, then W transpose of X plus B is less than 0. We'll multiply +1, then it is greater than 0, and if it is multiplied by negative -1, then it is less than 0. And the requirement is, for this equation, there is a requirement. We have a requirement in support vector machine. These are our margins right? What we want is, when we classify a point, when we make a classification, when we make a classification, we want the classified point to be at least 1 unit away from the margin. The distance between the margin and the point classified, this is the distance. The distance should be at least 1 unit away from margin. We want to add this constraint now, at least 1 unit constraint. Distance should be 1 unit away from the margin. We want to add this constraint. I will call it as constraint. We are constraining, we are restricting that at least 1 unit away from the margin. We have to add this constraint to our function. So that will be yi of w transpose of x plus b should be greater than or equal to 1. This is our new constraint now. We have added the constraint. And this constraint is known as canonical constraint. Constraint is known as canonical constraint. Right? So let's see this. I have explained you soft margin, right? Soft margin. Data will be overlapping. In real-time data, there is no hard margin. No data is perfectly classified. There is no hard margin. There will be overlapping of data. There will be overlapping of data. And in real world, you have to find the soft margin. And what I have mentioned here, soft margin. In soft margin, I have mentioned that data is overlapping. So there will be error or misclassification. So there will be error or misclassification. And here I have mentioned the classified data should be at least 1 unit away from the margin. For this we have added this constraint that is known as canonical constraint. So our equation is this. And now we want to add one more constraint, that is overlapping of data. In real world, data overlapping. So we have to find the soft margin because of overlapping. Because of overlapping, there is error. What is error? Error is nothing but misclassification. So we want to add this error to this equation now. We want to add the error. We add the error. Our equation will be yi of w transpose of x plus b greater than or equal to 1 minus error epsilon of I. This is the error. We got the equation. So how we will interpret the error? Let's interpret this error. There are three conditions. If error equal to 0, if error error is greater than 0 and less than 1. If error is greater than 1. So these are the three cases of the error. What if error is equal to 0? That means there is no error. If error is equal to 0, that is there is no error. That means correctly classified. Machine has correctly classified. No misclassifications. And if the error is between 0 and 1, and if error is between 0 and 1, I will show you with graph as well. That would be a good understanding. Correctly classified, no misclassification if error is 0. Data are correctly classified. No error. And if error is greater than 0, less than 1, this means correctly classified, data is correctly classified, but data is inside margin. Data is inside margin. How this will look? What does this means? Data is inside margin. Classification is correct, but data is inside the margin. And third condition, if error is greater than 1, error is greater than 1, this means misclassified, very high error. That means data is completely misclassified. Data is misclassified. What will be the diagram for this? Data is misclassified. See, X is here and 0 class is here. Data is misclassified. Error is equal to 0. Data is perfectly classified, no misclassification. And if error is between 0 and 1, data is correctly classified, but data is inside the margin. And if error is greater than 1, it is misclassified, completely misclassified. That means see, it has interchanged, it has wrongly classified. Okay. So with the error term or final equation, we can write the error has our equation. Based on this condition, error equal to 0, error between 0 and 1, and error is greater than 1, we can write this equation as error equal to max of 0, 1 minus yi of weight transpose of x plus b. This will be the final term we got, error term. This will be our error term. Okay. We have derived our error term here. This is our error term. And to this error term, we should have a control over this error. What is the control? What do I mean by the control over the error? We will add a parameter C. This is known as hyperparameter. We will call it as hyperparameter. We will add this value to our error term. Let me first explain what is this C means. What is this C means? If C is large, then classification rate should be high. Classification rate should be high. Margin is small if C is large, and if C is small, classification rate will be low. Means there are misclassifications, and margin is wide. Margin is wide. Looks something like this. If C is large, margin will be thin, will be small, and makes prefers more perfect classifications. And if C is small, it will be margin will be wide. The margin will be wide. It makes misclassification. It is okay to make the misclassification, but it wants wider margin. So you have to decide the C value. C value is hyperparameter. It is you want to lower the error or you want to keep the error more, but you and margin large. That is based on your project requirement. Okay. So what the equation? How to add this C parameter now? Our equation, our error term was this, right? Error equal to max of 0, 1 minus yi w transpose of x plus b. So if we add this error term to all the errors in our data point, every data point it has classified as an error. The error. So we want to add error to all the terms. That means summation of I is equal to n 1 to n is equal to 1 to n. For all the data points in our data set, there will be error. To this error, we will add a hyperparameter C to control the error based on your project requirement. Whether you want a wide margin, more error, more misclassifications, small margin, and less misclassification. Based on this scenario, you have to decide the C value. You have to decide the C value. So this is the term. And what is our error? If we expand the error, C summation, sorry for that. C summation of I is equal to 1 to n. Error is max of 0, 1 minus yiw transpose of x plus b. This final term, this term is known as hinge loss. This is known as hinge loss. So we got our hinge loss. We have focused on the hyperplane. We have focused on the hyperplane, right? From the hyperplane equation, this is the hyperplane equation, W transpose of x plus b. We have added the function if it is greater than 0, plus 1, and less than 0, minus 1. Plus 1 is classification, like one class and the other class, positive class and negative class. Then we have added a constraint that the classified point should be at least 1 unit away from the margin. This constraint is known as canonical constraint. So it should be at least greater than 1 unit away from the margin. So we have added greater than or equal to 1. And this is known as canonical constraint. And in real-time data, there will be soft margin, there will be data overlapping. Because of overlapping, we will have an error or misclassification of the data points. So we have to add this error to our hyperplane, to our canonical constraint now. So when we add this error, it will become, the equation will be this 1 minus error term. And the error term, we have three cases. If error is 0, that means machine has made correct classifications and there is no misclassification. And if error is between 0 and 1, machine has made correct classification, but the classified data points are inside the margin. And if error is greater than 1, then machine has made completely wrong classifications, misclassified. The data points are not correctly classified. So based on these scenarios, we add the error term. We make the error term as max of 0, 1. So we are selecting the max of 0, 1. And to control the error, whether we want our for project requirement is we want a perfect classification task. Even if the margin is small, then C value we should C is a hyperparameter. You have to select the C value. If you want classification rate to be high and margin to be small, then we go for C is large. We will give a larger C value. And if you want the classification rate to be low, you are okay with certain misclassifications, but you want your margin to be wide, your margin to cover larger area, then you prefer C as a small value. Select a smaller C value. So adding this hyperparameter, our equation will be C is equal to summation of error. Summation of error is for every data point, there will be an error, and we are adding all the errors in our model. It will be C summation of I is equal to 1 of error, summation of error. And summation of error, it is same C, summation of error. I have just rewritten the equation. Error term will be this. So this final term, this is known as, final equation is known as hinge loss. Okay, so this is completely from the hyperplane. So now we will focus on margin. And if you check the equation of margin, what is the equation of margin? If you see, the equation of margin is the 2 divided by absolute value of weight vector. 2 divided by absolute value of weight vector is our equation for margin. Margin is equal to 2 divided by absolute value of weight vector. So, but I will rewrite this equation, margin equation has, I will inverse it and square it. Because why I have squared it? To get the positive value. To get the positive value, I have squared it. And why I have inversed it? Because it is easy to derive. It will be easy to derivative purpose. If you make the calculations using the derivative, it will be easy for me. So I will just inverse and square the margin equation to get the positive value. So this term is important. Margin equal to 1 by 2 absolute value of weight vector square. And what is our hinge loss? Hinge loss is C summation of I is equal to 1 to n max of 0, 1 minus W trans P plus X. Okay. This is margin and this is hinge loss. Now, combining this equation, both the equations, I will add both the equations. That will be my cost function. Cost function for support vector machine. So my final cost function for support vector machine will be J of W equal to so this is the cost function. Using this cost function, we have to find the minimum cost function. Using this cost function, we have to find the minimum cost function to find the best hyperplane for our machine learning, for our support vector machine. So the support vector machine will use this cost function to derive the best hyperplane. So this is how support vector machine will draw a hyperplane to make the classifications. Now I have explained you linearly separable data. This data is linearly separable. Even if it is overlapping also, okay, we can find something. See, even if it is overlapping, okay, we can separate at this point. We can find this. But in some cases, in some datas, all the datas are not linearly separate. All the data sets are not linearly separable, right? Not linearly separable. So what to do then? The data set is not linearly separable, then how to draw the hyperplane? How to draw the hyperplane? What will be the hyperplane if data is not separable? Then the support vector, if data is not separable, then the support vector machine will fail. Will fail. It is not linearly separable. That is not the case. That is not the case. When the data is not linearly separable, sorry, when the data is not linearly separable, there comes support vector kernels. The support vector machine will use the support vector kernels based on the data, based on the classification. What are support vector kernels? Support vector kernels are mathematical functions. There are just mathematical functions used to solve complex classification problems. Support vector kernels are mathematical functions used by support vector machine to solve complex classification problems. Complex classification problems. I will give you some examples of how the data is might look when you plot it. This is linearly separable data. In some cases, the data might, the classification, the data might be like this. data might be like this. And in some cases, the data might look like this. These are possible scenarios. Data might be like this. You cannot separate it. You cannot linearly. These are not linearly separable data. You cannot make the hyperplane here. What we will do in this scenario is we will use support vector kernels. Support vector kernels. What the support vector kernel do is, support vector kernel will transform the data. Will transform data into high dimensional space. Support vector kernel will transform the data, will make the data transformation into high dimensional space. To make it, why it will make the transformation? To make it linearly separable. See, this data the machine has. We have given this data to the support vector kernel. We have given this data to the support vector kernel. To demonstrate what this kernel will do, it will transform this data into higher dimensions. Now it will make 3D. This 2D, this was 2D, it will make to higher dimensional space, 3D. And it will split the data. It will transform the data. See. X class is in this plane and O class is in this plane, other plane. So you can make the classification. You can draw the hyperplane. You can draw the hyperplane here to make the classification. This is what the function of. This is the function of support vector kernels. This is how the support vector kernel works. So there are different types of kernels in support vector machine. And for every support vector kernel, there are different equations. I will give you few examples of those. Okay. Let me write in a table for kernel equation and decision boundary. That is hyperplane. Okay. Kernel equation and decision boundary. First most popular kernel, that is linear kernel, which we have seen here. For linearly separable data, we will have a linear kernel, and its equation is xi of t x of j. Okay, this is for how the hyperplane, how our decision boundary will be. It will be straight line, that is hyperplane. Okay. And second type of kernel is polynomial kernel. The equation for the polynomial kernel is xi of transpose of xj plus c to the power d. D is the degree of polynomial. X square, x cube, x to the power 4. And the hyperplane, how the hyperplane will be? It will be curved. Hyperplane will look like curved hyperplane. And third is RBF kernel. The equation for the RBF kernel is exponential of minus gamma, exponential of minus absolute value of xi minus xj square, absolute value of xi minus xj square. This is the hyperplane will be highly flexible hyperplane. It will like 3D, 4D dimensionals. It is very flexible and it is non-linear. It is non-linear. And fourth type of kernel is sigmoid kernel. Fourth type of kernel is sigmoid kernel. It is, and the equation for sigmoid kernel is tan h alpha of xi plus xj, xi transpose of xj plus c. Sorry, even I don't remember these equations. I'm just giving you to demonstrate. Okay, to like at least we have the basic understanding how the equation will be. And the hyperplane will be kind of neural network. Will be a kind of neural network line. I cannot draw and show you those if it's not possible. If you want to go in depth of this, you can search on other platforms. But I will show the practical demonstration how to use these kernels. I will definitely show you the practical demonstration of these kernels in the upcoming session of this video. But for now, you understand the kernels are the mathematical functions used by support vector machine to solve complex classification problems. This is linearly separable data. In real world, the data might look like this, or the data might be like this. To solve such complicated classification problems, what support vector kernel does is it will transform the data into a high dimensional space to make it linearly separable. For example, this data will be transformed into 3-dimensional and we will draw a hyperplane. This is hyperplane. The kernel will draw a hyperplane. It will find out a solution to make the hyperplane, and the equations and the types of kernels and equations and how the hyperplane will look is for linearly separable the equation and the hyperplane is normal hyperplane, which I have demonstrated. And the polynomial, it will be curved, RBF it will be highly flexible, and sigma it will look something like neural network line, and these are the equations for hyperplane. Okay, so see here we have the gamma value, we have the alpha value, we have the degree value. This we will do in the hyperparameter tuning. I will also do the hyperparameter tuning in the grid using the GridSearchCV in the upcoming practical session, where I will show you how to specify these values and find out the best parameters. We will use this kernel. Okay. So this completes the support vector machine theoretical concepts. Now let us start the practical session. I have built a project. I will demonstrate you. So I have built a breast cancer classification using a support vector machine. Cancer rate is growing. There are many kinds of cancer. So I have used the breast cancer data set. It will classify whether the patient has the best breast cancer or patient is doesn't, or the patient doesn't have the breast cancer. I have built this model using the support vector machine. The data I have downloaded it from Kaggle. This data is downloaded from Kaggle. After loading the data, if you see that this is diagnosis, I will provide you the data. I have provided you the data in the GitHub. Okay, you can download it from the GitHub. I will provide the GitHub link in the description. Diagnosis here in the data, the diagnosis is the target variable. if we see the brief analysis of the data, see we have 32 columns here. 32 columns. The first column, see ID. This is not required for us. And the 32 column, see the 32 column unnamed, and it is full of zeros. This is a non-null value, like 0. It is full of zeros. This is just an dummy column. It is an I don't know why this column is there in our data. So I have dropped these two columns, ID and unnamed, both the columns. And what are the other columns? Radius mean, texture mean, perimeter mean. What are these values? See, for the breast cancer, how the medical test will be, they will take a tissue from the breast, and that tissue contains many cells. For each cell nucleus, they are calculating this, they are measuring this using the medical diagnosis, doing the medical test. They are identifying the values of the cells, radius, texture, perimeter, area, smoothness. They are using these values, they are finding out these values from the cell, and they will make a decision from these values of cell. They will make decision whether the patient has the breast cancer or patient doesn't have the breast cancer. And if the patient has the breast cancer, they are called it as, in the medical terms, these are medical terms, benign. Sorry if my pronunciation is wrong. Benign. That means non-cancer. Tumor is not detected in the tissue. And if the diagnosis term is M, that is malignant, then the patient has the cancer. The cell has detected, the medical test has detected the cancer in the cell. Malignant, if it is M, it is cancer, and if it is B, benign, it is non-cancer. Patient doesn't have the cancer. So our data is categorical here. You see M and B. This is categorical data. So I have labeled this. I have done the label encoding to convert this data into numerical. For malignant, if the patient is cancer, it is 1, and if patient is doesn't have the cancer, it is 0. Okay, so it is binary classification. 0, no cancer. 1, has cancer. I have converted it into numerical value. So after converting the numerical value, what I have done is I have taken, there are 30 columns. I can't show the 30-dimensional diagram for you. So I have done a 2-dimensional diagram to see how the data is classified. I have used the radius mean, the column, x-axis, and y-axis has concave points mean. This is the y-axis. And plotted hue. See, hue equal to diagnosis. Diagnosis is our target variable. So I have plotted a scatter plot using the C-bar. You see the x-axis is radius mean, and y-axis is concave points mean, and hue. That means these classification points, I have colored them with 0 and 1. 0 red points. These red points are non-cancer, and the blue points are cancerous. These are cancerous points. You can make this looks a linearly separable data, right? We can linearly separate this and make the classification. And one more point to observe here is, see, there are overlapping of points, red and blue. So there are overlapping of points. What does this mean? Overlapping of points. The hyperplane which our machine going to draw will be a soft margin. It won't be a hard margin. It is a soft margin hyperplane because we have overlapping data points, and this looks linearly separable for when we consider two features, radius mean and concave points mean. So let's build the SVM model. Let's do it. Target. And before building the model, I have to check whether data is balanced or imbalanced. I have shown you also how to handle the imbalanced data in the logistic regression video. The link will be in the description. Okay, you have to go through the logistic regression video and check how to handle the imbalanced data if there is imbalanced data. So if I do the distribution, if I check the distribution, for non-cancer we have 357 data points, and for cancer we have 212 data points. So it's almost balanced data. See, if we plot the distribution, it looks balanced. It is somewhat, non-cancer is 60% and cancer is 40%, 60 and 40%. So okay, I don't do the handling here. I don't do the handling of imbalanced data set. I will directly go for building the model. So we have to first split the data X. I will consider all the other columns except the target variable, and Y I will consider only the target variable, our diagnosis. Then I will train test split. I will split the data into training and testing with 0.2. Test size is 0.2. That means 80% of my data will be trained data and 20% of my data will be test data, and random state is equal to 42 is it will select the 42 records random state, and stratify is equal to Y. Stratifying equal to Y, that means Y variable, because I have the ratio, because the data is 60:40. It is not perfectly balanced. So I want my both Y train and Y test to have the same ratio of data when I split the data. So Y train should also contain, like if Y train has 10 records, 6 records should be non-cancerous and 4 records should be cancerous. And in Y test also, if Y test has 10 records, 6:4. I want to maintain the same distribution. So I have used stratify equal to Y. Now I have to scale the features, fit and transform. I will scale only the input features, and I will do the fit transform for the train features. That means median and my standard deviation is, mean should be 0 and standard deviation should be 1 of my scale. I will bring all the input features on the same scale and I will fit that data. But the test data I will only scale, transform it. I don't fit it because I don't want the leakage, data leakage. To avoid the data leakage, it is very important you only transform the test data, not to do the fit and transform. So first I will build baseline linear support vector model. That means baseline model. My baseline model is linear support vector model, not polynomial or RBF or sigmoid. I will use the kernel as linear. See, yes, support vector classifier. Again, the support vector machine model is from Scikit-learn library. SVM import support vector classifier. And kernel, I have specified kernel as linear. So base model, I'm building a linear support vector classifier model, and I will fit the data, X train data and Y train data. After fitting the data, after fitting my model, after training the model with the training data, I will make the predictions and evaluate. Again, the classification report, precision, recall, confusion matrix, ROC, AUC score, everything I have covered in logistic regression video. You should go through the logistic regression video to have the deep understanding of the performance metric for the classification task. So I have plotted the classification report. See, it's the accuracy is too high, 0.96. Our accuracy is 0.96. We are not focusing on the accuracy or something here, because the project is to learn the SVM. The project is to understand the how to implement, how to use the SVM, what are the terms of the SVM, like kernel, see the kernels. We are understanding the SVM. So don't more be specific about the accuracy score. Accuracy score, the best accuracy score should be between 0.85 to 9. I will choose 0.8, that is 80% to 90% is a good accuracy model. And if there is 0.96, there is overfitting of data. If I visualize the hyperplane, that is decision boundary, using two features. Let's see how our hyperplane looks. See, support vector machine has drawn the hyperplane to separate the data. The thick black line. I will enlarge this image. This line is best fit. These are our two margins. This is going away from the zero. Above zero is positive. Red points are positive and Y points are negative. That is, yes, the blue points are non-cancerous, red points are cancerous here, data points. And it has built the hyperplane like this. And see those support vectors. Some points it has also drawn the black circle around those points for blue, if you see closely here. These points, these are on the margins, right? These are support vectors. Margins, best fit line, and support vectors. You can clearly see how, like, for the real-time data, how it is looking. But considering only two input features, I have drawn this. For these two input features, this is linearly separable data. But I can't say for entire data set it is linearly separable or what. So I will use now support vector kernels, because I don't know, right, whether it is linearly separable or it is how the data is classified on what basis, because we have 32 input features, because we have 30 input features. So I will use different kernels now. I will train SVM with different kernel. First I will, as usual, I will train with linear kernel. Here one point to notice is, see here, I have used C equal to 1. I told you when doing the theory, hinge loss, I will add a hyperparameter. I have shown you there. See, C is a hyperparameter. If it is large, classification rate and margin, I have explained this concept to you. This is hinge loss. So C hyperparameter. You have to select this. I have told you. So I am selecting here 1. C is equal to 1. Now consider it as 1. It is not like too much or less, just 1 unit. I will demonstrate how to use different C values in hyperparameter tuning. So for linear model, I am using C parameter, hyperparameter as 1, which will control my error. And also I have done the polynomial kernel. See here, only the kernel name has changed to poly. And in the poly means degrees. X1, x square, x cube, x4. What is your degree of polynomial? So I have used the degree as 3. And again, I have kept same hyperparameter as C is equal to 1. And I have trained the model. I have trained my support vector classifier model. Next kernel, I have used the RBF kernel. Right, RBF kernel. And C is 1 again here. C is 1. And gamma, I have used one more term here. See, gamma is equal to scale. What is gamma? Let me explain you what is gamma. gamma is equal to scale. I have used it here. I will explain you. Gamma RBF kernel. RBF kernel, there is a minus gamma value here. You see minus gamma value. I will rewrite, no worries. RBF kernel equation is exponential of minus gamma absolute value of xi minus xj square. This is gamma. And there are two ways. First is, what is gamma? What is gamma? Is gamma. Gamma controls the influence. Gamma controls the influence of each training data point on decision boundary. Gamma controls, gamma controls the influence of each training data point on when creating a hyperplane. Or decision boundary. Gamma controls the influence of each training data point when creating hyperplane. That is the gamma in RBF. And there are two ways to find gamma. One is scale, second is auto. So for the scale, we'll calculate gamma as gamma equal to 1 divided by n into variance of x, where n is number of data points, number of features, number of features, that is columns. We have 30 features, I think. Yeah, 29. One is target variable, so we have 29 features. And variance of x. Variance of x is variance of data. Variance of data. This formula is used to find gamma. If we specify gamma equal to scale. And there is another method that is auto. To find gamma, there is another method that is auto. It is simple formula. Here the gamma is equal to 1 divided by n. N is number of features, number of independent variables or number of columns. Simple. Gamma is equal to 1 by n. So these are two different ways of finding the gamma. Okay. I have specified for RBF kernel, I have specified gamma equal to scale, and I have trained my model with RBF kernel. Next is sigmoid kernel. So again, sigmoid is equal to 1, and I have just kept the hyperparameter as c is equal to 1, and I have trained my model SVM sigmoid. Let's make prediction and calculate the accuracy of each model I got. Okay. And I have sorted in ascending order. RBF kernel has high accuracy, that is 97%, 0.97, 97%, followed by linear, sigmoid and polynomial. Polynomial kernel has very least accuracy, 0.88, that is 88%. So this is what I got by trying different kernels, by training the model with different kernels. Kernel equal to linear, kernel equal to poly here, polynomial kernel, and kernel equal to RBF kernel, and sigmoid kernel. So with different kernels, after training the SVM model with different kernels, I got the RBF support vector machine with high accuracy, that is 97%. So RBF kernel is good kernel. I can say RBF is a kernel I would prefer. So this is how you have to use the kernel. So this is very long process, right? Like building, fitting the model with different kernels. Every time you have to write the code. Every time you have to build the model, train the model, and then you have to make the prediction, and then you have to plot the accuracy and check yourself which is the best model. And also you have we have specified here only c is equal to 1. For only c is equal to 1, we are getting that accuracy. Maybe c for lesser c value, or maybe for greater c value, the model accuracy might improve or might decrease. We don't know which is the best c value. And I have used here only gamma equal to scale. It might be gamma equal to auto will give you the best accuracy. Who knows? Who knows? And c is equal to some other value, and degree is equal to some other value. Here c is equal to 1 and degree is 3. But c is equal to, let's see, c is equal to 0.1, lesser c value, and degree is equal to 5. For this degree and the c value, if I change the degree and c value, our polynomial kernel will give the good accuracy. There are scenarios, there are consequences, there are scenarios, different scenarios. So to handle the different scenarios, I will do the hyperparameter tuning using GridSearchCV. What is hyperparameter tuning? What is hyperparameter tuning? Hyperparameter tuning is to train model with different parameters. Not the model, I will say train base model. Train base model with different parameters. Parameters will differ for different algorithms. Parameters are not same. For support vector machine, you have seen the kernels. For support vector machine, the parameters are, we have kernels, c value, gamma value. But for decision tree, it is different. For logistic regression, it is different. You have to decide what parameters you want to select, what parameters you want to tune your model. Train the base model with different parameters. Find the best parameters. What are the best parameters? Parameters with which the model accuracy is high. Parameters with which the model accuracy is high, those parameters will be the best parameters. You have to use that model. This is how you have to tune your model. That is this is hyperparameter tuning. Hyperparameter tuning. And if you see, I have mentioned here GridSearchCV. What is GridSearchCV? For every parameter, different parameters for kernel. See, for kernel example, I have list linear, poly, RBF, and sigmoid. For C value, again I will give as 0.1, 0.001, 1, 10, 100, lower value to higher value. So these are grids. So when you do the hyperparameter tuning and you specify the grid, this is grid search. What the machine will do is, for linear model, it will check all the values of C. 0. For the linear, specifically for linear, it will check 0.1, 0.001, 1, 10, and 100. Then again for poly, it will check different values of C and find the best parameter for poly. Then for RBF, it will check all the values of C and find the best parameter. For sigmoid, again it will do the same. So this is known as grid search. It will search for best parameter for your model. It will do the grid search. It will go one by one and do the searching. And also I have specified here grid search CV. What is CV? What the CV stands for? CV is cross validation. Cross validation. What we do when we are building the model, we do the train test split, right? In our project, we have done 0.2, that is, see, project we have, when building the model, we have split the data. We have split the data into train and test. See, test size is equal to 0.2 and we are splitting the data into train and test, right? 0.2. So what the CV does, how the data is split now? This is data set. It is split into train and test. Okay. So this is 20% and this is 80%. This training data, I have told you in the linear regression, this training data will further split into training and validation. Training and validation. So CV is cross validation for every training. When it trains, when it trains linear with 0.1, when it trains linear with 1, when it trains linear with C is equal to 10, for every training, it will validate, it will check what is the accuracy of the model, whether it is improving, decreasing. It will check, it will evaluate, every time it trains. So we have to specify this CV in the grid search CV. We have to specify the grid, kernel, C, gamma, our values. Okay, we have to give the list of values. Same time, we have to specify the CV also. We have to specify the CV value. It might be 2, CV is equal to 4, CV equal to 5, something like this. Let me specify because in my project also I have defined CV is equal to 5. Cross validation is equal to 5. So what does this do? Is your data set, training data set. Now it will split the data. This is validation data set, this is training data set. Again, in the next step, the next training section, it will again split the data. Training, validation, validation. Training, validation, validation. Validation, training. Sorry. Validation, training. Training, validation. So it will split the data in these chunks. These chunks, it will split the data, validation, training in the first epoch, in the first training. And in second training, this will be the validation and this is training. This is validation and this is training. So it will split the data. It won't just test the data without splitting it. It will again split 5 times if I define CV is equal to 5. And for every step, it will evaluate the model and it will calculate the accuracy. Suppose at the first, second, third, fourth, and fifth. Suppose for the first, our accuracy is 97%. Second, we got the accuracy of 98. Third, we got the 99, 97, 97.4. We got the accuracies for every training and validation. When our CV you have specified as 5. So it is training 5 times and evaluating 5 times. And let me specify here, it has kernel is linear, C is equal to 1. For kernel linear and C is equal to 1 and cross validation equal to 5, it has trained your model 5 times and evaluated your model 5 times and you got the 5 accuracies, and the final accuracy for the kernel linear and C is equal to 1, our final accuracy will be average of all the training sets, all the cross validation sets. So the average will be 97.4%. Just this is random, I have not made any calculation here. So the final average will be 97.4%. So this will be the accuracy of your model, final accuracy of your model. This is how it will, your cross validation model will find the accuracy. This is the hyperparameter tuning you have to understand. Hyperparameter tuning, train the base model with different parameters and find the best parameters where the model accuracy is high. And this is known as hyperparameter tuning. And what is grid search? You have to specify the grid which the model has to search and do the training on different parameters. You have to specify the different parameters, that is grid search. And cross validation is 5 is for every training it will evaluate. You have to specify the cross validation value. If you specify cross validation as 5, it will make the 5 trainings with different, by splitting the data in different chunks of validation and training and find the accuracy. Then it will calculate the average of that accuracy, which will be the final accuracy of the model. Okay, so this is the hyperparameter tuning I have done here. So again, from Scikit-learn, sklearn.model selection, I have imported the GridSearchCV. I have also imported my base model SVC, support vector classifier. I have specified my model, SVM model, defined my model. So now I will build the parameter grid. See, I have to define the parameter grid. I will define the kernels. Kernel is linear, polynomial, RBF, and sigmoid. And C value, that is my hyperparameter. I will give different values. 0.01, 0.1, 1, 10, and 100. Then gamma value, I have explained you the hyperparameter also. I have explained you the kernel also. I have explained you the gamma, how the gamma value will calculate. Scale and auto. And then the degree. 2, 3, and 4. See, degree is not in linear, degree is not in sigmoid, degree is only for polynomial kernel. Gamma is only for RBF kernel. But still we are giving the GridSearchCV. How it will make the calculations? So the machine will automatically detect C kernel, and C is for hyperparameter is for all the kernels. But gamma it will go only for RBF, and the degree C it will go only for poly kernel. It won't apply the degree. It won't consider the degree values for other kernels. It will detect that. Now I will run our GridSearchCV. I will create the GridSearchCV object first. Before training the model, I will create this GridSearchCV object. We will define GridSearch is equal to GridSearchCV. What is the estimator? It will be the support vector model, support vector classifier, which I have defined here, SVM model, support vector machine model. And param grid is, what is my grid? This is my grid. It is a dictionary. See, kernel is key and values are list of these values. And C is key and values are this. So this is a dictionary. You have to give the dictionary. Param grid is equal to param grid. And cross validation. See, I have mentioned cross validation is equal to 5. So you have to evaluate every training. You have to train 5 times and evaluate those results. And the scoring I have chosen accuracy. You can choose ROC, you can choose precision, you can choose recall, you can choose F1 score. I have chosen the overall accuracy of the model because I am not mainly focusing here on the accuracy or performance metrics. My focus is on hyperparameter tuning, demonstrating hyperparameter tuning and support vector machine. So the scoring is equal to accuracy I have chosen, and n jobs is equal to 1. And how many times you want to check your model? How many times you want to test it with the actual test data? I have chosen only 1. Okay. So if you train, if you fit the model, now I will fit the model. The model training starts. Here the model is training, train GridSearchCV. After training the model, I will look for the best parameter. What are my best parameters? So this term, best underscore params underscore GridSearch dot best underscore params underscore will give you the best parameter. My best parameter is C is equal to 1, degree should be 2, gamma equal to scale, and kernel is RBF. If you are using polynomial, degree is 2. Otherwise, C is 1, gamma is equal to scale, kernel is equal to RBF. This is the best model after hyperparameter tuning. These are the best parameters you can use to build your model. And what is the score of the model? Accuracy score, that is 0.97. 97% the accuracy of your model. Did you get this? So this is the hyperparameter tuning. So we have covered support vector machine, hyperplane, support vector, support vectors, margins, cost function, hinge loss. Then the support vector kernels you have to find out, and how to use those kernels. I have demonstrated the practical implementation. I have also shown the practical implementation. The notebook I have provided here in my GitHub. I have uploaded the notebook, project description, the data, everything. So you can download the notebook from here and practice the code. So that's all for today. This is the support vector machine learning algorithm. I hope you have a good understanding. I hope you had a good experience. Thank you very much.